Hello there and welcome back to Science with a Coffee. This is lesson 3 on drawing Bohr-Rutherford diagrams. In this video, I'll be breaking it up into 3 major parts. The first part will be on understanding the different aspects of subatomic particles for the diagrams, then the conventions on how to draw the diagrams, and then we'll go over some examples. I'll also be making a practice video, so I'll show some practice examples that you should try on your own, and then I'll make a separate video going through those answers. Now, let's kick it off here with this table. This table has the 3 major subatomic particles. So we have protons, neutrons, and electrons. Their charge and their mass. Now, protons have a charge of +1. So they are positively charged subatomic particles, and they can be found within the nucleus. And they weigh 1 atomic mass unit, or AMU. Now, this is very important for when we're actually figuring out what elements we're drawing and how many protons they have. Then we have neutrons, as covered in lesson 2 on the atomic theory. Neutrons are neutral, or they have a charge of 0, so it's neither positive nor negative. However, they do still have a mass of 1 atomic mass unit, or 1 AMU. And we have electrons. They have a charge of -1, so it is kind of the opposite to a proton, and their mass is relatively 0. So I have the approximate symbol there, which is the 2 squiggly lines. Electrons do weigh something. They do have a mass, however, it is so small, it is negligible compared to the mass of a proton or a neutron. So for the math that we'll be doing for drawing Bohr-Rutherford diagrams, we can just assume the mass of an electron is 0. So that covers the charges of protons, neutrons, and electrons, as well as their mass. So we can move on to the conventions of how to draw a Bohr-Rutherford diagram. For the second part, we're going to be going over the conventions on how to draw and what we need to know to understand drawing a Bohr-Rutherford diagram. So the first thing we need to know, and again, I will give you this information for these different examples because we haven't gone over the periodic table yet. So the first thing you need to know is that the atomic number equals the number of protons. So I'm just going to write that. So the atomic number equals number of protons. So this is how we'll know how many protons each atom has. Then the next thing we need to know is that the atomic mass is composed up of protons plus neutrons. This is basically the nucleus of the atom. So if I have the mass of the protons, and this is an AMU, and the mass of the neutrons, also an AMU, as we've covered in the first section of this video, we add them up and you'll get the atomic mass. And for all of these examples today and the practice ones, they will all be neutral atoms, but something you should keep in mind is that with neutral atoms, number of protons will equal the number of electrons. As I mentioned in the first part of this video, protons are +1, electrons are -1, so if it is neutral, you'll have the same number of these in the atom. And the last thing we need to know for a convention or guideline is the different shells or energy levels of the atom. You can have 2 electrons in the first one, you can have 8 electrons in the next, and then you can have 8 electrons in the third, and then typically you go up to calcium, and that will have 2 electrons in its outermost shell. So again, it goes 2, 8, 8, and 2. And I'll explain that a little bit more as we tackle the periodic table. So we can use this information when we go through our examples. Let's give it a sip. All right. So we are going to use again carbon as the example. So I'm going to be giving you the information you need to know from the periodic table, just so I don't have to tackle that just yet. but don't worry, we'll be going over that very soon. So for carbon, what we need to know for carbon is a few simple things. First, its atomic mass we're going to use today is going to be 12. Now, typically carbon does weigh 12, and that again is AMU. The next thing we need to know about carbon is its atomic number is equal to 6. So with this information, this is what we would get typically from the periodic table. However, since I haven't gone through that, I'll just give you these numbers so that you know exactly what you need to draw the Bohr-Rutherford diagrams. If carbon weighs 12 and has 6 for its atomic number, what we know from our conventions is that the atomic number also equals the number of protons. So the atomic number is 6, which also means it has 6 protons, and each proton weighs 1. If each proton weighs 1, then 6 plus the number of neutrons must equal 12. If you rearrange that equation a little bit, you will have the atomic mass minus the number of protons equals the number of neutrons, or if you really like algebra, then it's 6 plus x equals 12. X has to be 6, or 12 minus 6 is 6. Either way, we have 6 neutrons. So the next thing we have here is 6 neutrons, and we got this by the atomic mass here minus the atomic number, which is 12 minus 6 is equal to 6 neutrons. Simple enough. So now we know we have 6 protons, 6 neutrons. Now we're going to be drawing a neutral atom of carbon. You can just assume they're neutral unless you're told otherwise, which will mean we have the same number of protons as we have electrons. So that means we have 6 electrons. So with that information, we can now draw carbon. Its atomic symbol is C, and we know it has 6 protons, 6 neutrons, and 6 electrons. So how do we draw the Bohr-Rutherford diagram for carbon? So we start by drawing the nucleus. So the nucleus is going to be a circle. Inside this circle, we have protons and we have neutrons. So we will have 6 protons, and you just write the number and then the letter capital P. And then you have 6 neutrons. So this makes up the nucleus of the atom. So this has all the mass of the atom in it, as we found from Rutherford's experimentation. So that is the 6 protons and the 6 neutrons taken care of, and that adds up to the atomic mass of 12. Now we just have the electrons left. With the electrons, we know that we can have 2 electrons in the first, and then 8, and then 8, and then 2. So right now, we're going to fill up the first shell. I add 1 electron. You can add them as a dot. You can also add them as an X. It really doesn't matter. For consistency's sake, I'm going to add in dots. And then the next example, we can draw X's. It doesn't matter. So now we have 2 electrons. And this first shell is done. Now we can move on to the next one. So we have to draw another circle, which is a lot harder than you think. In this, we have a total of 6. We've already drawn 2, so that means we're going to have 4 electrons left. Now, how I do this, it can be different than how you do this, and that's fine, but the way I do it makes sure that you don't makes any simple or stupid mistakes with counting your electrons, and also it helps you get ready for grade 11 and grade 12 or the IB or whatever it is you're going to be studying after this with chemistry. And that is to draw your electrons by themselves first at like 12 o'clock, 3 o'clock, 6 o'clock, 9 o'clock type thing, if it's a clock. So I now have 1, 2, 3, 4 electrons, so I still need 2 more. And there's one, and there's the other. So now I have 2 electrons in the first shell, 4 electrons in the outermost shell as drawn here. This adds up to a total of 6 electrons. So that is the Bohr-Rutherford diagram for carbon, and that is all you need. So we have the protons, the neutrons, and the electrons here. Now with this diagram, it's important to know that you can abbreviate protons to P, neutrons to N, and electrons you can draw it as dots or X's around the outside. Now again, as I was saying before, I typically keep my electrons spaced out, and we'll do another example that will have more electrons in it so you can see kind of how all that pairs up. So let's jump into our next example. For our second example, we're going to be using silicon, which is basically carbon's bigger brother. It has an atomic number 14, and with that information, we know that it will have 14 protons. So its atomic number, as I said, is 14, and its atomic mass is equal to 28. So with that information, we know that we can take 28, subtract the number of its atomic number or the number of protons, either way it's the same thing, and we'll have 14 neutrons. Now, since we're drawing a neutral atom of silicon, our number of protons were equal to the number of electrons. So this time we're drawing 14 electrons. So slightly larger atom. So again, we will start with our nucleus, and you will draw a circle. And this time we have 14 protons and 14 neutrons. For those of you who are thinking ahead, we'll have 3 shells to go through. So 2, 8, and then 8 is the maximum numbers of electrons in those shells. So we can draw our first shell here kind of neatly, and we can have 2 electrons there. Now we have 12 more electrons to draw. So we'll need another shell because that first one can only fit 2. This next one we know can fit 8. And since we know that we need to draw a total of 14, we're definitely going to be filling these 2 completely. So again, 1, 2, 3, 4. This way we know we have 4 there, and then I double them up. So as I alluded to in our first example with carbon, I left them at kind of the 12 o'clock, 9 o'clock, 6 o'clock, 3 o'clock. This is because it's much easier to keep track of and count once you're done. So I have 1, 2 in the first, and then 2, 4, 6, 8 in the next. If you space them all out, it's just really, really difficult to count them, and sometimes you make silly mistakes and forget one or miss one or add one too many. This way, it's nice and organized and you won't make those silly mistakes. So now we have 8 here and 2 in the first. That brings us a total of 10. However, silicon has 14, so we need to add a total of 4. So now, to count again, 1, 2 in the first, 2, 4, 6, 8 in the second. That brings us to 10, and then 1, 2, 3, 4. So now we have 14 electrons. Yep. We have 14 neutrons. We have 14 protons. And if you add up our protons and neutrons here, you will get the atomic mass. And then our protons is equal to the atomic number. So that is the Bohr-Rutherford diagram for silicon. After this, I'll give you a couple of practiced examples, and then I'll take those up in a later video. For your practice problems that I'll take up in the lesson 3 practice video, I would like you to try to draw helium, nitrogen, and sulfur. So try these out, see if you can do them, then take them up with me in the practice video. That brings us to the end of lesson 3 on the basics and conventions of drawing Bohr-Rutherford diagrams. Again, as I mentioned, I will be making a practice video on helium, nitrogen, and sulfur if you wanted to try those out and take those up in the next video. After this, I'll then cover the periodic table basics, and then that will be lesson 4. And as always, I will end it with my 3 things. So the tip this video is time management. It's always very important to manage your time well. So time management is very important, and it will help you stay on top of all the different things as you keep getting more and more responsibilities as life goes on. The photo today is from Lençóis in Brazil. All my Brazilian friends will probably make fun of my pronunciation of it, but it's Lençóis Marianas, something like that. Anyways, I'll put the spelling below as well. Beautiful, beautiful place. If you do go there, please try not to destroy the area because it is a one-of-a-kind place. There's nowhere else in the world that's quite like Lençóis. Then your band this week is one of my all-time favorites, and that is Radiohead. If you don't know Radiohead, you should definitely check them out. And if you don't like whatever you try a different CD because they've been around a while and they have many different styles of music that have slowly changed throughout their discography. So anyways, time management, lovely picture of Lençóis that I took, and definitely check out Radiohead. So if this video helped you or you liked it, please like, hit the bell so you can get notifications for future videos, subscribe, and as always, be the ball.